Here we go, Spartan fans, section 2.1, rates of change and limits. For this lesson, you will want graph paper, your book, and your calculator. Okay, so the first thing we're going to do is learn a new parent function that I believe is probably new to you. And it's called the greatest integer function. And it looks like such, INTX. And it is known as the greatest integer function. On your calculator, math, let's see here. Math, arrow over to NUM, number, and then number 5, INT. Okay. So really what it should be called is the lowest integer function, or sometimes it's called the floor function. Okay. All right. Our little table of values here. Essentially, it means what is the lowest integer in relation to the number that you're plugging in. So if X is 1, Y is 1. And if X is 2, Y is 2. And if X is 3, Y is 3. You get the point. Ha ha, get it? Get the point? It's so funny. What happens in between 0 and 1 and 1 and 2, etc. That's what's of interest to us. If X is, let's say, 1.7, the integer below, the floor, the integer below 1.7 is 1. And plug in 1.8. The closest integer below 1.8 is 1. And if you plug in 3.4, the closest integer below 3.4 is 3. The closest integer below 3.7 is 3. So every number that I plug in, let's go back to 1. 1.7, 1.8, 1.9 is going to give me 1. 1.4 is going to give me 1. 1.6 is going to give me 1. Every number between 1 all the way up to 1.9999999. So as I get close to 2, that would be an open circle. And once you get to 2 itself, the integer, the value of y, will be 2. And 2.1, 2.2, 2.3, 2.97, blah, 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 all the way up to 2.999, yada, yada, until you get to 3. You jump up to 3. So sometimes it's called a step function, can be called a floor function. I think greatest integer function is actually deceiving. That's what it looks like. Step function, floor function, greatest integer function. Take a minute to plug that into your calculator. Again, that's math number 5. And when you graph this, let's do a zoom 6. And it looks like a bunch of steps. Okay, so that is the greatest integer function. Let's go back and review geometric series, and we had started to talk about convergence. So let's go back to that. And I had said it was your introduction to calculus. Well, guess what? Here we are. You're given, well, let's just start with 1 plus 1/2 plus 1/4 plus 1/8, etc., etc., etc. Okay, this is a convergent geometric series. What makes it convergent? The value of these terms are getting closer and closer and closer and closer to 0. So the value of the first term was 1. Sorry, AT, whatever. The value of the fourth term, 1, 2, 3, was 1/8. The value of the 10th term, I can figure out by plugging in 1/512. Let's write a formula for the sequence. So the sequence is going to be the first term, which is 1, times r, which in this case is 1/2 to the n minus 1. And what happens is, as n gets large, t sub n gets small. We're going to write that in what we call limit notation. So what we're saying is the limit as n gets really large, infinity, the value of this sequence, the summation is the series, the sequence is the list of terms. The value of this sequence, which is 1/2 to the n minus 1, is equal to 0. Okay, and let me write it out. How do you say this in English? When you learn about logs, it's very specific. You don't say log 2, 3. You say log base 2 of 3. Same thing with limits. The limit as n, x, whatever, as n approaches whatever number it's going to be. In this case, it's infinity. Of, in this case, 1/2 to the n minus 1 is, and in this case, it was 0. So that's how you would say this in English. The limit as n approaches infinity of 1/2 to the n minus 1 equals 0. Now, let's keep in mind something's really big here. And this big thing is it's getting small. Will it ever actually be 0? Will the value of these terms ever be 0? Well, your calculator will say so. But theoretically, the answer is no. It'll just be super, 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 super small. And that is a limit. So a limit is a value. What is a limit? A limit is a value that a function approaches but such bad handwriting, but may or may not ever equal. This is an English definition. This is not mathematical. Asymptotes. Asymptotes are great examples of limits. You approach an asymptote, but you can never touch it. let's take a look at some graphs and practice finding limits and what does it mean to approach but not touch, etc. And does it always have to be an approaching value? Can it be an exact value? So let's draw a graph and we'll clear up a lot of that. Here is some random piecewise graph. Take a moment, I'll pause the video and you can draw it. And you know what, I just changed my mind. Let's make this an open circle at 8, -2. Okay, so we're going to talk about limits here and exact values and what that looks like. Okay, so you have some function. I'm just going to randomly call this the f of x. If I ask you to find the f of 2, this is the exact value. The exact value of the function, if I plugged in 2, I would get 3. And I will note that that is referred to as the exact value. Right. Let's find out what is the f of 8. Okay, well, if you look, there's an open circle at 8. So, oh, it says 8, -2. So isn't the exact value -2? And the answer is no. The exact value in this particular case doesn't exist. So we say it's undefined. This is where a limit comes in. The f of 8, which I have here is -2, it's undefined. However, the limit exists. If I'm sliding down, think of it as a slide, and I'm sliding down, I'm approaching -2. If I'm on the right-hand side here, if I'm sliding down, I'm approaching -2. So the limit exists even though the exact value is undefined. And that would be written as the limit as x approaches 8 of the function is -2. You can approach a limit, you don't have to touch it. For an exact value, you have to touch it. So this is what I was saying in the definition that it may or may not equal. So undefined, but I can approach it. This leads us to another question about the right hand and the left hand. So if you recall, I said, oh, well, if I'm sliding down the slide here, I'm approaching -2. Not falling in, that's good, I'm approaching. And if I'm sliding down here, I'm approaching, that's -2. What I just did was I approached -2 from the right-hand side. I approached, sorry, I said I approached 8, my apologies. I'm approaching 8 from the right. I'm approaching 8 from the left. Don't be confused. My hand is moving the left towards the left, but it's my right hand. I'm starting with right hand moving, left hand moving. So those are called right hand and left hand limits. Those of you who have not the best handwriting, you're going to need to learn how to find better handwriting. The limit as x approaches C, it's a superscript with a negative sign. This is referred to as the left hand limit. And conversely, the limit as x approaches C with a superscript of a plus sign, that is the right hand limit. And if there's no superscript of plus or minus, that would be the overall limit. Okay, let's take a look at what's happening at -1. At -1, I have an asymptote. At -1, I have an asymptote. This is the best part about limits, evaluating these graphs. I think it's so fun. Okay, so the exact value does not exist. No, undefined, bad language, it's undefined. So the f of -1 is undefined. Exact values are undefined, limits don't exist. Exact values are undefined. Limits don't exist. That's the proper language. Some people say no solution, I'm not solving anything. So exact values, if it's a problem, they're undefined, and limits don't exist. When you're learning vertical lines, and I ask you what the slope of a vertical line is, and people say the slope is vertical. No, it's not. The slope is undefined. The line is vertical. Like horizontal lines, the slope is 0. The slope is not horizontal. Language. So we know that the f of -1 is undefined because it's an asymptote. However, it does have limits. And what's interesting about this graph is that it has different limits depending on which side you're approaching from. So let's look at the limit of this function as we approach, I'm getting really good at the whiteout. The limit of the function as, and let's do -1 from the right. The limit of this function as we approach -1 from the right. Just got done talking about bad handwriting, and here we go. Okay, the right-hand side, I'm coming from the positive values of x, and I'm moving in the negative direction. So as I'm coming from the right, I'm getting closer and closer and closer and closer to -1. What's happening to y as I get closer to -1? Well, y is going up, 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 which is infinity. The limit as x approaches -1 from the left. So -1, and then the superscript is negative, so from the left. So I'm going from the negative, and I'm coming from the left-hand side across. So what's happening to y? So as I'm getting closer and closer to -1, y is getting down, y is approaching negative infinity. Okay. We have that the exact value is undefined. We have the limit from the right is infinity. The limit from the left is negative infinity. So what happens now? I don't even know what part we're on. I missed a part. F, G, H, whatever. P, Q. I missed a part there. So what if I ask you now about the overall limit? What do you think that's going to be? Take a second. If the right hand is going to infinity and the left hand is going to negative infinity, where's the overall limit going? It doesn't exist. The right hand must be the same as the left hand. The right hand must be the same as the left hand. Let's try and write that in as a little summary. How about this? If the limit as x approaches c from the left of the function does not equal the limit as x approaches c from the right-hand side. Oh, this fancy lingo you're learning. If the left doesn't equal the right, oh, it's an if-then statement, then the overall limit does not exist. And lots of times we'll just use DNE, does not exist. Mathematicians were lazy. We like to have abbreviations for everything. Okay. So exact values, if they're not around, if it's they're undefined. If there's an open circle, if there's an asymptote, they're undefined. Right-hand limit, moving from the right across towards the negative direction. Left-hand limits, moving across towards the right. In this particular case, right hand, left hand, good to go. At the asymptote, right hand, not the same as the left hand, doesn't exist. And that's for a graph. But I hate to tell you this, you're not always going to be given a graph. Let's look at some properties of limits. So you are going to want page 58. I'm not going to list all the properties of limits. They're on page 58. I am going to walk you through some of them though. So I'll do this more as just an oral exercise. So you have the limit as x approaches c of some function is equal to L. And the limit as x approaches c of another function, and that equals m. So I have my book here. I'm just going to go through and explain it. If you add, so the limit of the, let's get that a little bit better. Okay, hopefully you have your book in front of you. Add the function, so the limit of the sum of the functions is the sum of their limits. The limit of the difference of the function is the difference of their limits. The limit of the product is the product of the limits. Like, I think that most of this is self-explanatory. If you divide the functions, you divide the limits. One that's going to be pretty useful for us is this constant multiple rule. So I'm going to actually write that one out because we're going to use it. It's going to come up quite a bit. So the limit, this is the constant. I'm just reinforcing this one because it's going to show up more than the other ones. So the limit as x approaches c of some constant times the function is equal to that constant times its limit. All right. And then on page 761 is this thing called the sandwich theorem. So this one I'm going to write down, but in case you are a little bit lost or you want to go back, we're on page 61. And I sometimes take for granted that I think, well, this is pretty obvious, but what's obvious to me may not be obvious to you. So you have a function g and a function h. You got a function g, you got a function h, and sandwiched in between those is some function f. This is why it's called the sandwich theorem. You have a function g, you have a function h, and somewhere between those two pieces of bread, we just smashed our function f. Okay. If the limit as x approaches c of the g of x is equal to the limit as x approaches c of the h of x. G and H both approach C, and they're the same. They have that same limit L. If that means that the limit as x approaches C of the f of x is also equal to L. That is the sandwich theorem. Again, it's in the book. Wanted to show that to you. Okay. How do we find limits without a graph? I'm aware that this is a lot, but there's going to be long videos, long lessons from now on. It's a lot to get through. Okay. Is that crooked? Oy, oy, oy. Sorry. How do you find a limit without a graph? Okay, well, the nicest, easiest way is to use algebra. So we're going to find the limit algebraically. So let's say I ask you to find the limit as x approaches -3 of x squared plus 4x minus 2. No denominator, no problem. Not a log, not a root function, no problem. You have to worry about issues with limits if there's a denominator, a log, a root. These cause problems. This is a parabola. The limit is going to be the same as the exact value. The limit is going to be the same as the exact value. Plug in. 9 minus 12 minus 2, -5. I'm using my calculator because I don't want to mess it up. That's it. Finding a limit algebraically is just a matter of plugging in. What about the limit as x approaches 5 of x squared minus 25 over x minus 5? Uh-oh. I try to plug in. This is a 5. I try to plug in. I can't. But I can simplify. This is the same thing as the limit as x approaches 5. There is a lot of rewriting. Don't be lazy. You can skip the factoring and reducing step if you want, but you cannot go straight from here to give me the answer. You have to show that you have reduced. So this is going to be x plus 5. Difference 2 squares, factor, reduce. This is 10. Notice that the exact value is undefined, but the limit exists. This right here would be something like here. Exact value is undefined, but you can still approach the whole. It's exactly what you just did. So I'm not going to do a ton more examples about that because I feel like it's just a matter of plugging in, which I think you can do. We will do one more with an integer function, which is still new to you. The limit as x approaches, how about 3/7 of the integer function. I missed the t. Okay, so think of it as the floor function. 3/7, the closest integer less than 3/7 is 0. Okay. Finding a limit on your calculator when you don't know how to graph the function off the top of your head, etc. We are going to do probably the most common function limit that you're ever going to see. If I ask you to find the limit as x approaches 0 of the sine of x over x. Cool. Plug in 0. Doesn't help me. I can't factor and reduce this. There's no funky substitutions. So what am I going to do? I'm going to use my calculator. So the first thing we're going to do is we're going to graph the sine of x over x. Radians, not sure that we're going to be in degrees much actually anymore. So when you're in radians, oops, it looks like such. It's not really a great picture. And I want to know what's happening as x approaches 0. So I'm going to go ahead and change my window. So if I want x to approach 0, I'm just going to go from -1 to 1. See what it looks like. That's not a very good picture. And you know why it looks bad? Because I'm supposed to be in, I did radians and it doesn't look very good. It looks like a horizontal line, which clearly it is not. It is clearly not a horizontal line. So actually, I'm just going to go back to my standard window. I'm just going to do a zoom 6. When all else fails, do a zoom 6. All right, and that looks like a wave. Certainly looks like a wave. And when you look at the calculator, it looks like when x is approaching 0, y is approaching 1. And it looks that way from both the left and the right. So from the left, it looks like I'm approaching 1. From the right, it looks like I'm approaching 1. You know what? Let's look at our table. Okay, and my table, I guarantee you, looks way different than your table. But at 0, it says error. My x values are very different than yours. But at 0, it says error. So what I would like you to do is, second window, go to your table set and have your delta table 0.25. So I'm going to go by 0.25. Look at your table, and here we go. So x is negative. As x goes from the left, negative values, to the right, it does look like we're approaching y is 1. Again, the exact value is undefined, but it does look like I'm approaching 1. Let's change our table and make it even a better view of what's going on. So let's change our table to, how about 0.01? And I'm going to do my table start at 0. So now I've got really small increments. Well, look what's happening. It does, it looks like it's approaching 1 to me. Doesn't it look like that to you? I'll just pretend you're saying yes, since I can't hear you. So the exact value is undefined, but the limit exists, and the limit from the right is equal to the limit from the left, which in this case is 1. This is going to come up a lot, okay? This is going to come up quite a bit. So let's do an example algebraically that we don't have to use our calculator for, but it looks a little bit funky. You're gonna say, wait a minute, how can this limit exist? Because algebraically, when I plug in 0, I get undefined. Okay, this will be the last one. This is going to be the limit as x approaches 0 of x over x plus sine x over x. Using, I think it's the sum property, the limit as x approaches 0 of x over x plus the limit as x approaches 0 of sine x over x. Well, what's x over x? X over x is 1. So this is the limit as x approaches 0 of 1. And we just did the limit as x approaches 0 of sine x over x. This is going to come, I mean, this is going to be, you put in your arsenal of knowledge for calculus. We just figured out this was 1. The limit as x approaches 0 of 1 is 1. This is a horizontal line. So for all values of x, y is 1. So this is going to be 1 plus 1. That's the most complicated 1 plus 1 you've ever done. The answer is 2. Congrats, your first real calculus lesson.